with the starting time. If we
okay, you can start. Thank you.
On YouTube. Okay.
Yeah. Okay. Thank you very, very much. It's a pleasure for us. Now, have a good presentation. Thank you very, very much.
Thanks a lot. Welcome everyone to the 8th session of SIGraDi 2021, day 3. Now we will have a session focusing on intelligent practices and processes. There will be 5 remarkable presentations in this session. After watching the presentations, the question and answer part will follow these presentations. Now we are starting with the first presentation titled Robotic Weaving Manufacturing of Optimized Glass Fiber Panels, a study by Thomas Vivanco and Philip Yuan. And please, I would like to share my apologize for any misspelling or mispronunciations of the names throughout the session. Thanks for your understanding. So we can continue with the first presentation.
Good afternoon, I am Thomas Vivanco. I will present the article Robotic Weaving Manufacturing of Optimized Glass Fiber Panels, reading with Philip Yuan from Tongji University, China. Composite materials offer a wide range of uses in construction. The flexibility to make different shapes, the mechanical properties, and extended useful life make them high-performance materials with comparative advantage over other conventional materials like aluminum or iron. The application of reinforced plastic with carbon glass fibers have been very successful in the aerospatial and in past year in the ag industries, offering the advantage of having the same and in some cases better mechanical properties of components for a fraction of its weight compared with conventional materials. This advantage had opened new design possibilities of architectural components, opening the development of computational design and robotic fabrication processes to manufacture efficient material systems. Buga and Elytra pavilions, both developed by researchers from the University of Stuttgart, present a clear path of the integration of design, simulation, and advanced robotics technologies and processes that can lead to a non-standard three-dimensional structure. Almost impossible to manufacture with common materials and processes because of its persistence, energetic, and structure efficiency. From a computational design perspective, each fiber can be understood as a vector, where the internal mechanical forces can be homogeneously distributed through the components. Creative design for topological mechanical optimization in 2 dimensions of vector forces had been successfully deployed in the Bionic project developed by the Living in 2016, where the goals were to decrease in 30% the weight of an Airbus A320 internal partition. One of the negative aspects of petrol-based composite materials is their harmful impact on the environment of their manufacturing and their low second life extension possibilities after the original use, reducing its circularity. Nevertheless, advancing development of reinforced fibers polymers based on lignocellulosic fibers combined with basic digital manufacturing formulas as a complementary tool for manual processes like weaving. Both manufacturing techniques, manual and advanced robotics, offer a wide spectrum of possibilities for composite materials. The integration of both processes might allow the serial production of personalized, prefabricated structural components. This research proposed a straightforward computational design and robotic manufacturing workflow to produce energy-efficient and high mechanical performance fiber panels with common digital fabrication equipment like reactive milling machine. This Four elements were designed. First, composite mixture definition, roving fiberglass filament, polymeric resin recipe composed by initiators, promoters, accelerators, and retardants, and support metrics. Second, a custom CNC welding tool, design and development of a custom and universal welding tool that can adjust to almost any CNC machine that can have constant tension over the fiber and wet the fiber with the polymetric resin in a liquid state in a pulsion processes. Computational design for mechanical simulation and topological optimization based on machine learning of structural fiber panels. And fourth, fabricate physical prototype with 3-axis CNC milling machine adapted with a custom welding tool. There are general recommendations as reference value for the polymer fiber rigid matrix, but as the curing process is done with ambient temperature, it is necessary to develop empirical tests to ensure stable, comparative, and desired results to the different environmental agents that might affect the mixture composed by initiation, promoters, accelerators, and retarders. Also, to include manufacturing variables like machine movement, speed, quantity, and density of the vector, both with a direct incidence over the time period. By modifying a common three-axis milling machine to manufacture the panels, the workflow can be applied in almost any laboratory or place that don't have high technological equipment as robotic arms. To standardize the manufacturing processes, the custom welding tool must ensure the stabilization of the resin mixture and apply a constant and precise moisture over the roving 2400 ESP filament. Both requirements were accomplished by integrating the pulsion process into the tool. Starting from the basic planner panel, the goal was to stimulate the application of mechanical loads in different vectors, positions, and fixed vertices. The combination of efforts was applied over the three scenarios. First, a vertical load horizontally applied over the total extension of its per edge. Second, a combination of lateral and vertical loads in the same geometric plane. And third, considering only its weight with a fixed interior edge. The prototypes were done by randomly calculating the interior panel and superior edge with fixed points. In a finite element analysis software, the mechanical properties of glass fiber were applied to the model, measuring the von Mises stress. The values were fed into the topology optimization model to have a distributed and balanced stress over the vector, reducing the displacement and elastic phase. First physical prototypes were produced at 40 by 40 centimeters and 80 by 40 centimeters matrices. The first with fixed point in the four edges and the second one only in the upper and lower edges. This was done to test the direction and turning radius of the tool that can ensure the tension of the fiber and the precision of the fiber direction. Each anchor point represented a point in the simulated and optimization diagrams. Optimized vector lines were converted to a G-code toolpath, which was loaded to a 3-axis CNC machine with a custom welding tool. Final prototypes were fabricated using the custom tool based on the computational design optimization workflow described. In the given design, the fabrication matrix with all the possible vector combinations to the optimization process. A limited number of vectors were reduced considerably to achieve a stable mechanical performance of the panel, decreasing the amount of used materials. This means that 100% of the used material is performing, making the system smart in the sense that there is zero accumulation of non-active material. At the same time, the digital manufacturing process can produce flexible, fast, and efficient varieties of panels with a low investment of equipment. In order to manufacture one-to-one scale prototypes, backend studies and different fiber thicknesses should include in the simulation analysis. Also, measurements of the physical prototypes must be developed to compare them analytically with the digital prototypes. Also, as to thank this research process, intern student from Pontifical Catholic University of Chile, also the Hub House team, and the Digital Futures Group, PhD group from Tonji University. Thank you very much.
Now the first presentation, we watched the first presentation. We continue another interesting one titled The Assembly and Fabrication of Double Curved Panel Structure using Japanese wood joint created by desktop 3D printers. Okay. Can you all see the screen?
Hello, my name is Kei Atsumi from
Yes, Emma, we can, and the sound is perfect. Thank you.
Assembly and fabrication of double curve panel structures using Japanese wood joints created with desktop 3D printers. This research presents a new direction for free-form structure assembly and fabrication through the collaboration of 3D printing and Japanese wood joinery. Instead of using digital fabrication machine to match the architecture scale, this study uses a fused filament fabrication FFF desktop 3D printers, which is the most widespread and inexpensive printing solution. The project demonstrates how artisanal knowledge integrates with 3D printing architecture production by reconfiguring joint geometry, parametric modeling, 3D printing fabrication, and cell-build assembly processes. Past few years, digital fabrication was making innovative design and manufacturing possible for more and more people, especially in architecture production. New methods of joining and free-form modeling are being researched from various perspectives. Previous research has shown that the formability and compatibility of digital fabrication with parametric design tools has a proud impact on the creation of free-form geometry and complicated morphology in architecture production. There are two main fabrication ways used in digital fabrication research project: the subtractive method and additive manufacturing method. With additive manufacturing, the use of large industrial 3D printer has enabled the efficient production of buildings with curved shapes. Previous study has shown that the potential of large industrial 3D printing to reduce the human labor, construction time, and the cost associated with this architecture production. Nevertheless, there is a weak point regarding printing accuracy and structural variability after construction. At the same time, this expensive equipment is not suitable for viable open construction system in digital fabrication. But the FFF desktop 3D printer is the most widespread and affordable printing technology, and it has not yet been fully studied as a viable construction method. Additionally, the compact FFF 3D printer can fabricate free-form and complex shapes more accurately than large industrial 3D printer. In this context, it might be hypothesized that desktop 3D printers can overcome the weakness of the building production tools used in previous research. So, when we create big envelope using small machine equipment, it is necessary to output multiple components and assemble them, and the joining techniques are very important. Japanese wood joints are simplified joinery for traditional wooden architectures that do not use glue or metal fittings. The joining geometries are limited by old school fabrication technology, but we can easily create complicated joinery to the double curved panel components by using FFF desktop 3D printers. The goal of full-scale self-built prototyping is to evaluate the value of desktop 3D printers for the fabrication of free-form structures and explore the possible use of Japanese wood joints as a method for the detachable assembly of double curved panel components. For the methodology, the design and manufacturing tools has entirely under control by authors. This study was carried out in 4 major steps. First, Japanese wood joint reconfiguration. Second, parametric 3D modeling. Third, fabrication by FFF desktop 3D printers. At last, self-built assembly practice. For the joint design, we focus on how to reconfigure the Japanese wood joining rules and geometry with 3-dimensional thinking. We propose 2 joints for floor to shell components and for shell structure components. For the floor and shell components, we took reference from the Hozo and Sen in Japanese wood joints. For the shell structure components, we used Ryakukama and Sen as a reference. Through the physical test prototyping, the accuracy of the joint geometry was verified. We use Grasshopper, which is a parametric modeling tool in Rhinoceros for optimization of panel components. By adding the complex wood joints geometry to the double curve panel components, we were able to create digital 3D data for detachable freeform structure architecture components that are tightly fixed without use of glue or metal fittings. Approximately 1,000 unique pieces of digitally generated components were printed by 6 FFF desktop 3D printers running in parallel and 24/7 for 8 weeks. The self-built assembly experiments were carried out for open construction system. The overall structure was assembled by 4 regular workers and 1 designer. The self-built assembly experiment was completed in 6 hours without the use of glue and metal fittings. Because of the high level of geometric accuracy of the 3D printed components, the fitting of the components was quite accurate. The result of this project showed that the FFF desktop 3D printer is a viable fabrication tool for the production of architectural scale for freeform structures, and the Japanese wood joints technique can be integrated as a 3D printed assembly method for modularized freeform architectural components. Instead of relying on huge architectural scale digital fabrication machines, this research project was the first attempt to realize a full-scale freeform detachable structure through the combination of desktop 3D printing technology and Japanese wood joinery reconfiguration. However, we must mention some limitations. The 3D printed panel assembly method to real-world construction is still limited by building regulations. Further experiments and practices are needed to improve the joining function against various forces and to improve structure resistance and fire protection and insulation performance of the components. Once we overcome these limitations of desktop 3D printing production, we might get new evolution for architecture production and design. Thank you for listening to our presentation.
We have followed the second presentation. So, okay. Not only giving a clear understanding about the state of the art in digital fabrication, but also providing insights about the future directions of interrelations among tools, techniques, and materials. We have followed 2 interesting presentations. Even the cats accompany me in this moderation. Now the third presentation is coming, titled "The Design and Fabrication of Variable Facade Panel Systems" by Taner Thiessen and Nilüfer Emami. Yes, screen sharing always takes maybe 2 more seconds delay, but we are almost there.
Good day. I'm Tanner Tyson. Nilufar Imami and I are excited to share our paper titled The Design and Fabrication of Variable Facade Panel Systems. This study shares the process and findings of year-long research on the design and fabrication of precast elements used in facades. This study began with an assessment and classification of variability between panels on selected built facades, and then transformed into a design exercise with the goal of advancing precast panel production processes. The need to adjust and make better precasting processes stems from the fact that contemporary designers have the desire to produce complex masonry facades. While these complex designs can be realized in new and constantly evolving CAD software, architectural production processes are lagging behind. Precasters are struggling in particular to produce geometrically varied products without fabricating a large number of molds. This practice can lead to a significant increase in project costs and production time. However, the utilization of advanced technology could help counteract these inefficiencies. Specifically, the utilization of additive manufacturing paired with thoughtful mold design can allow for precasters to rapidly produce molds with relatively low labor. Current research to those regards can be called digital fabrication of concrete, which is either focused on the direct creation of concrete objects using digital fabrication or on the creation of formworks for concrete using digital fabrication. For example, studies have been done on the feasibility of utilizing big area additive manufacturing in the production of formworks for precast panels, and the results were very promising. The cost per pour was lowered because the formworks are reusable, and the labor required to fabricate the complex formworks were reduced because of the automated printing processes. Given that fact, we developed the belief that the creation of formworks with additive manufacturing is a worthwhile pursuit, and decided to focus on the production of variable panels with alternative molding methods. There are many contemporary facades that have varied concrete panels. 2 specific projects are pictured because they have a number of interesting panel variants. The Le Veron building in Paris, France, which is composed of a concrete lattice facade, is on the left. The Perot Museum of Nature and Science in Dallas, Texas, which is composed of an incredibly large number of panel variants which evoke geological striations, is on the right. After observing both those facades and a number of others, common trends between the variations present were noticed. We came up with 3 different definitions in order to classify that variability. Ornamental variability occurs when panels have the same overall geometry but a range of different ornamentation on one or both of their surfaces. Geometric variability occurs when panels have a range of different measurements for their final cast panels. Specifically, the measurements of the outer boundaries of the panels change. Assembly variability refers to the panel's qualities upon on-site assembly. Similar to a brick that is agnostic to orientation in certain axes, a panel with assembly variability has a design that allows for it to be placed freely on a facade to create a number of different overall facade arrangements. The design is ambiguous enough to place the panels anywhere on the facade without compromising the overall design. After first studying and then synthesizing strategies to create variability present in contemporary facades, it was our turn to begin designing a panel we're affectionately calling Panel A. The design process we undertook differed from a traditional panel design process in that we were simultaneously developing both a design and a fabrication strategy. Our goal with Panel A was to mimic the aesthetics of the Le Veron building while allowing for variability to be created during the fabrication process. In practice, this involved the segmentation of the panel design into a square grid, and the organization of the lattice geometry so that every block of the grid would meet at the same points. Here is a demonstration of the results of our studies. The developed molding method allows for varied panels to be produced from a singular mold, which can be reused. This was achieved through the careful consideration of fabrication constraints before, during, and after the design process. For fabrication of the mold, Formlabs 3D SLA printers with a flexible resin were used. The segmentation of the design into a grid allowed for the mold to be fabricated in separate pieces that are both rotatable and interchangeable in the mold tray. With this strategy, a multitude of panel variants can be produced from a singular mold as the printed formwork can be reused and rearranged. Once the fabrication strategy had been developed, we decided to expand upon it quite literally. Panel B was designed around the idea of expanding the grid of mold pieces to a 4x4 size. Unlike Panel A, however, Panel B's geometry was not organized around the placement of points at which the segments could meet. Rather, the pieces were designed so that in certain orientations they would produce a continuous geometry. That being said, the pieces are still interchangeable and rotatable, and so you can create an unorganized geometry if such was desired. In fabrication of mold B, a clear and non-flexible resin was used. Unfortunately, this resin was less forgiving when removing supports from the print, and as such, some pieces were destroyed in the fabrication process. Because of this, the built mold size was reduced to a 3x3 square grid. However, the desired effects were still the same, and the mold was able to produce a number of variants. To briefly recap, the designs of Panel A led to the creation of a variable fabrication method in response to the need to rapidly fabricate varied concrete facade panels. The conception of Panel A's fabrication method guided the production of Panel B through the expansion of the grid layout that organized the first design. Both molds were 3D printed out of different resins and both had reusable formworks that were interchangeable and rotatable, which is the principle that allows for the molds to produce a number of varied panels from a single mold. Although both molds were able to produce varied panels, the limitations of this method are not yet fully understood. Further studies will explore different fields like mathematics to apply principles such as aperiodic tiling patterns to the design of panels. This is a promising direction that can lead to the conception of more complex mold designs, which can still produce variable panels just as easily as those of this study. Thank you so much for your time. I hope you are as excited about the potential applications of additive manufacturing to the industry of architecture as we are. We'd also like to thank the NSF, LSU Discover, and the LSU School of Architecture for all the help that they have provided throughout this study. Thanks again, and have a great day.
Thank you for your never-ending interest. The session continues with another interesting study titled Wedge Kerfing, Design and Fabrication Experiments in Programmed Wood Bending. A study by Roberto Navoni and Dario Maroni.
Good morning to everyone. My name is Dario Marino. I am a visiting postdoc at STU Create Research Group at the University of Southern Denmark. The topic of this research is wedge kerfing, design and fabrication experiments in programmed wood bending. The research was supervised by Associate Professor Roberto Naboni, who also leads the research team at STU Create. In this study, we investigate material behavior and geometrical features of curved button. We implement the crafting technique of kerfing through robotic fabrication, and we develop a computational workflow to achieve programmed bending of straight and planar wood elements. The initial assumption is that current industrial processes to produce curved wood elements are often time-consuming, laborious, and therefore expensive. We experimented how kerfing can be used as an alternative wood bending technique. A kerf is a slit made by cutting with a saw, so the kerfing can be defined as the process of the strategic removal of material to achieve an elastic behavior of a solid material stock. Kerfing is used in various fields, from the making of musical instruments to product design, and we want to focus on the exploration of its architectural potential. Kerfing can be applied to both boards or linear elements. We focus on its application on wood buttons. These are among the most relevant contributions in kerfing for buttons. The first example shows how Kerfing is applied in combination with the other structural elements such as tension rods, while in the other two cases it is explored the elastic bending potential of this technique. We want to introduce the concept of wedged kerfing as a technique to produce curved wood elements without the use of molds. In this approach, the curved button is bent through the progressive insertion of trapezoidal wood wedges obtained from the production leftovers. Part of the research has been focused on the understanding of material behavior and limitations through preliminary tests. In the first place, we tested advantages and disadvantages of either expansion or compression curves. The main differences are that the expansion curves are relatively easier to fill with wedges, and there is no need for clamps during the gluing. On the other hand, compression curves have a better structural response and a lower risk of damaging the material when inserting the wedges. The second test was performed to understand what is the critical threshold for the wedges angles, and the results highlighted that over 6 degrees the wood would start to crack. The third test was done to see the effects of curve angle variation. The wedges angles have been kept in this case constant to 4 degrees. Intuitively, perpendicular curve would induce only bending, while the variation of curve angle would result in bending and twisting of the button. We'll now go through the computational workflow that has been set for this research. We start with an input geometry based on a set of control points used to generate a 3D elastic curve. Then we generate a quad mesh strip which is planarized and made developable as a straight strip through a physics-based approach. And this surface is then rebuilt and a recursive algorithm is set up to equalize the angles and extract the ruling pattern of the developable surface. The ruling pattern is then used to generate the robot toolpath. In the fabrication phase, the robotic cutting is based on this ruling pattern. In the assembly phase, the button is progressively bent after a moisturizing process through soaking, which brings the moisture content to about 20 to 25%, and the wedges are then glued. So this is an example that shows the process and the angles equalization for the curving pattern. At first, the angle of strip A vary from 0 to about 13 degrees, while in the next phase, the angles are equalized. This is also clear from the roll of strip A, where you can see the distance between rulings are kind of equalized, while in strip B, the distance is different because the angles are being made constant. These are images from the fabrication phase. The button is placed on table and clamped on the board underneath to prevent it to move, since while curving it would be more flexible. These are some of the prototypes that we realized with wedged curving. On the left are the buttons realized with compression curves, and on the right the one realized with expansion curves. This is a comparison of all the prototypes in terms of maximum and minimum bending radius and torsion, or to be more precise, the roto-translation of the first and the last cross-section. The prototypes have been scanned through a photogrammetry to analyze their deviation from the 3D model. This highlighted the fabrication tolerances and precision need to be improved. We also simulated the structural behavior of both expansion and compression curve, and as you can see from this graph, compression curving performs slightly better in both directions of the forces applied. This approach allows for a wide design space. As we can see in this diagram are shown some of the possible variations that can be obtained using just cylinder geodesics, while an approach with elastic curves is even more open. In conclusion, this research presented an investigation on material behavior and implemented a traditional woodworking technique through a computational workflow. Following this methodology, we have been able to program curved elements starting from straight buttons. Further investigation will be done on fabrication tolerances to improve the geometric accuracy and on mechanical tests to define better the structural behavior. This study is part of a wider research on wood bending techniques, which is currently ongoing at SDU Create. More specifically, we are focusing on the production of zipped buttons and boards to produce large-scale curved elements. These elements are realized through the robotic fabrication of interlocking layers based on analogous geometric principles of curving that have been presented in this research. Thank you. Good morning to everyone. My name is
Yes, the fourth presentation has already finished. Last but not least, we will continue with another inspiring study titled Biofaden 2.0 Pavilion, Experimental Study of Algorithmic Generative Design and Digital Fabrication with 3D Printing of a Bionic Pavilion Prototyping. A study by, I would like to apologize in advance for the mispronunciations. Juan Carlos Gulian Salas, Neander Furtado Silva, Luano Miranda Esper Calvas.
Olá, sou Juan Guilherme, sou pesquisador do Laboratório de Fabricação Digital e Customização em Massa da Faculdade de Arquitetura e Urbanismo da Universidade de Brasília e sou professor da Faculdade de Artes Visuais da Universidade Federal de Goiás. Hoje vou apresentar a pesquisa intitulada Pavilhão Biofaden 2.0, estudo experimental com projetação algorítmica generativa e fabricação digital com impressão 3D, de um protótipo de pavilhão biônico na região centro-oeste do Brasil. Esta pesquisa foi desenvolvida com a colaboração dos professores Neander Furtado Silva, da Faculdade de Arquitetura e Urbanismo da Universidade de Brasília, e a professora Luana Miranda Esper Calvas, da Faculdade de Artes Visuais da Universidade Federal de Goiás. Esta pesquisa corresponde ao segundo experimento de uma bateria de 7, os quais foram desenvolvidos dentro da minha tese doutoral intitulada Projetação e fabricação de pavilhão biomimético de forma complexa, celular e responsivo com tecnologias digitais e robótica em Brasília, DF, no contexto da produção de envoltórias arquitetônicas bioinspiradas, e onde a problemática foi determinar as possibilidades e limitações da projetação digital e da fabricação digital por adição de um pavilhão biônico em tamanho reduzido, onde a hipótese guia da pesquisa foi que a fabricação digital por adição, utilizando filamento fundido, é um processo de produção rápido e de pouca deformação e que permite a realização de formas complexas ou de geometrias não euclidianas. Assim, o objetivo da pesquisa foi determinar as possibilidades e limitações da projetação digital e fabricação digital por adição de um pavilhão biônico de geometrias não euclidianas em tamanho reduzido, e onde se observou que os softwares, rinoceros e grasshopper permitem projetar e prototipar estruturas de formas complexas. Esta pesquisa foi organizada em 3 etapas: etapa da fundamentação, etapa de materiais e logística e etapa da experimentação. Na etapa da fundamentação foram vistos conceitos sobre pavilhão, biônica, design generativo, fabricação digital e impressão 3D. Na etapa de materiais e logística, o material utilizado foi organizado em 8 categorias: espaço físico, mobiliário, equipamentos, softwares, material de escritório, material de impressão 3D, material de construção e ferramental elétrico. Na etapa de experimentação, foi organizado o trabalho em 4 fases. A primeira fase, que era do código gráfico de modelagem 3D digital do pavilhão. A segunda fase, operacionalização da fabricação digital do pavilhão. A terceira fase, seleção da tecnologia de fabricação digital por impressão 3D. E a quarta fase da fabricação digital e montagem do pavilhão. Na fundamentação, as definições utilizadas foram: para pavilhão, é uma instalação de caráter temporário para estudar metodologias de design digital, as propriedades dos materiais e as metodologias de fabricação digital. Para biônica, é o estudo das formas naturais para transferi-las à tecnologia. Para design generativo, é um método de design onde são estabelecidas regras e algoritmos computacionais para obter múltiplas soluções para um problema de design. Para fabricação digital, é um processo de fabricação utilizando máquinas controladas numericamente para a produção de um objeto com um material customizado. Para impressão 3D, é a tecnologia de fabricação aditiva que é capaz de produzir objetos ou estruturas tridimensionais a partir de um modelo projetado com assistência do computador. Na etapa de materiais e logística, podemos observar que o trabalho tem sido desenvolvido principalmente na infraestrutura da universidade e na residência. O trabalho da residência foi devido à necessidade que surgiu de fazer acompanhamento aos processos de impressão, os quais levavam um período de 4 a 9 horas de impressão contínua. Na etapa da experimentação, a primeira fase consistiu na preparação do código gráfico e modelagem 3D digital do pavilhão, a partir das frutas da atemoia, buriti, graviola e pinha, para posteriormente serem digitalizadas. A partir da digitalização das frutas, logo foram preparados os algoritmos generativos da superfície e dos módulos do pavilhão. Na segunda fase, se operacionalizou a fabricação digital do pavilhão. O pavilhão foi dividido em 8 panos. E cada pano foi dividido em blocos de módulos, em função da semelhança de tamanho. Nesta fase foi selecionada a tecnologia de fabricação digital por impressão 3D. Foram testadas duas tecnologias, a tecnologia de impressão por pó e a tecnologia por impressão de filamento fundido. Na tecnologia de impressão por pó, utilizamos materiais alternativos como a maltodextrina, gesso e açúcar de confeiteiro, a fim de diminuir custos. Este processo se apresentou como um processo demorado e que demandava muito cuidado. Na tecnologia de filamento fundido foram testadas duas impressoras, uma impressora que foi desenvolvida no laboratório de fabricação digital e customização em massa e uma impressora importada da China. Também foram testados dois filamentos, o filamento ABS e o filamento PLA, onde o filamento PLA se apresentou como a melhor opção para desenvolvimento do projeto. Na fase 4 foi realizada a fabricação dos panos em PLA e posteriormente foi realizada a montagem do pavilhão. Como resultado da pesquisa tivemos que o código da superfície do pavilhão permitiu a rápida modificação da forma e a determinação do número de módulos que seriam distribuídos ao longo da superfície. Que o código do módulo permitiu determinar o tamanho dos módulos, o tamanho do módulo, a forma do módulo, as faces do módulo e o tamanho das perfurações do módulo. Que um código do pavilhão permitiu a transformação da geometria euclidiana do módulo para uma geometria não euclidiana da superfície. Que o código do pavilhão permitiu preservar a proporção da espessura das faces em função do tamanho das mesmas faces. Que o tamanho máximo de impressão dos panos depende da escolha do módulo ou bloco, conjunto de módulos, possível de ser impressa na impressora 3D utilizada. Que a fabricação com PLA em uma impressora Happy é um processo de fabricação rápido, de boa resolução de impressão e com continuidade de adesão entre as camadas do objeto produzido, quando comparado com a impressão em ABS. Que o modelo 3D de tamanho reduzido do pavilhão é necessário para estudar e analisar as fases de operacionalização da montagem. Como observações a serem discutidas, temos que o código gráfico se apresentou como uma ferramenta versátil para o controle da geometria não euclidiana da superfície do pavilhão e da geometria euclidiana do módulo. Que o código gráfico permitiu modificar a forma da superfície do pavilhão e da geometria do módulo, mas ao modificar a geometria do módulo não modificava-se a geometria da superfície do pavilhão. Que o código gráfico permitiu preservar a espessura das faces do módulo em proporção ao tamanho das faces conforme o estabelecido no projeto. Que a impressão dos módulos ou blocos permitiu observar a necessidade de codificar as peças para serem organizadas nos respectivos panos e no pavilhão. Que o processo de impressão 3D por fundição de pó forneceu uma boa resolução de impressão em função da granulometria do material utilizado, mas é um processo demorado que demanda muito cuidado na manipulação da peça produzida até ela atingir a dureza desejada. Que a impressão 3D dos blocos permitiu verificar a necessidade de uma codificação no bloco para identificar a impressora na qual foi fabricado. Como conclusões, temos que se confirmou a hipótese guia do experimento, que a tecnologia de fabricação digital por adição, utilizando a fabricação por filamento fundido, é um processo de produção rápido e que apresenta pouca deformação nos objetos de formas complexas ou de geometrias não euclidianas. Que o processo de projetação digital, utilizando um código gráfico, permite a customização de formas de geometrias não euclidianas e euclidianas em massa e automaticamente, e guardando as proporções estabelecidas de projetação dos componentes. O tamanho máximo do pano e do módulo depende diretamente do tamanho da mesa de impressão da impressora a ser utilizada. Que a fabricação com PLA em uma impressora Happy é um processo de fabricação rápido, de boa resolução e de impressão com continuidade de adesão entre as camadas do objeto produzido. Que o modelo 3D do pavilhão em tamanho reduzido é necessário para estudar e analisar a operacionalização da montagem. Agradeço a coordenação de aperfeiçoamento de pessoal de nível superior CAPES, ao Departamento de Pós-Graduação da Universidade de Brasília, ao Laboratório de Fabricação Digital e Customização em Massa da Universidade de Brasília, ao mestre Leonardo Barreto e ao aluno Leonardo Figueiredo, pelo suporte fornecido para o desenvolvimento desta pesquisa. A seguir são apresentadas as referências utilizadas no desenvolvimento desta pesquisa. Obrigado pela atenção. Olá, sou
Thanks for the final presenters as well. It has been a quite rich session in terms of the used tools, the explored techniques, materials, and workflows, processes. And I think those experiments, experimental approaches provide valuable contributions to our understanding of geometry, material fabrication, as well as augmenting the affordance of what we already know. So thank you for all your interest. Now let's continue with the question and answer session part. Is there any questions that you would like to ask to the presenters? Of course, you can find further information in the proceedings and you can contact later, but it would be great to discuss online while we are together in that fascinating conference.
I'd like to start if it's okay.
Sure.
Hi, Sema. Hi, everyone. This is Nilüfer
Hello.
Imami from University of Illinois, and me and Tanner presented our work on concrete. There were two presentations that were similar in 2D printing parts that were assembled in a whole. It was the last presentation by Juan with 2D printed pieces, and also the presentation by Kei Atsumi, where they looked at 2D printing parts, but also looked at how they are connected to one another. And building industry is about putting different discrete pieces together to get a whole. So maybe we can start by discussing how Juan thought about the connecting the pieces together and how important is the connection, designing the connection versus designing the part itself.
So maybe I can talk first. Maybe you want to talk first. Okay. I will start. So my idea, come up with in Japanese with joint and 3D printing, small 3D printing is first. What if we, what if we can make detachable structure and also at the same time cheaper and also more affordable for every people. And also, if we focus on the joining geometry, it also, we can bring back the creation to the every people. So maybe I thought it's gonna be great for the future. What is creation for everybody? And right now, if we look at the 3D printing industry, everybody using like a huge 3D printer, and basically nobody cannot touch this equipment except specialists. So that's why I focus on joining and also creating small components and assemble them.
Thank you. Maybe before giving the word to Ayşegül, Joan, would you like to respond to this question as well?
Hi, nice to meet you. Sorry, but in this moment I have very soon in this place. I go to pass the question for the Professor Neander. Professor Neander, would you like to answer the questions?
Well, I think it's interesting the question about moving from parts to the whole, and I'm trying here to build a connection between the work of Juan and the work of Kay. Forgive me if I'm not pronouncing your name properly. And I was thinking, what is the parallel between the two works? Juan started with the fruits, with nature. And from the nature, he tried to build a module. While you start from tradition, the tradition of Japanese joints, and trying to build a connection with high technology. In this sense, this is the parallel that comes to my mind. One is drawing from nature into high technology, and you are drawing from tradition into high technology, which is, I think, is a path that is similar to arrive to a solution in construction. When you see a building, often the person who is lay on the subject thinks a building is a whole. He or she can see the pieces, and we, as architects, we always have to see the pieces because buildings are built by pieces, not as a whole. Now, perhaps one day it will be different, but so far as I can see, is always from parts to the whole. And so this is the parallel I'm trying to build between the two things. And I found very interesting as well the other paper about curving wood and curving in a sensible way, in a sense that you can, again, get something from nature, is a natural material, difficult to deal with, but you can establish a path in which you can get this material and connect it again with high technology, highly traceable, and very rationalized way, if I can say so. I don't know if I have answered the question that was put forward in the beginning, but I'm trying here to put the pieces together for the benefit of all of us.
Thank you. Ayşegül Hocam, in quotation.
Sema Hocam. Thank you very much. Those were really wonderful papers. Also, I was looking to the proceedings and I will read them. I just had a look at them all. I have a question to Kay. So sorry again, also if I pronounce it wrong. It seems simple, but it's so complicated at the same time. So it is very interesting to have the ability to take out the parts, of the parts, and then build our own, structure, maybe outside of our house by our desktop printers. Yes, but PLA filaments is not very eco-friendly. but the wood ingredient can be, has more potential out of it. But now I'm questioning its durability. Also, will it face with some difficulties? I think this research area is, I'm not very working on 3D printing. I'm not working on 3D printing or materials. Sorry if I'm mistaken, but as far as I know, there isn't any very big structure made of 3D printed wood right now. They made steel, they made concrete, they're working with clay. But I think this area is very, very promising case. So I really liked also your work. And have you ever thought about developing some also material studies or material computing, for example? My question is this. Okay.
Thank you so much. I think for the material, the wood 3D printing is still, haven't reached the, professional level in a way, because like for the concrete, clay, they all have fire protection, but for the wood fiber 3D printing material, it's quite easy to get burned, even though from brighter fire. So actually, I was trying to create some kind of new material, which contained wood powder, but still I haven't reached the promising level for the industry. But maybe I have some kind of a idea. Maybe if we can combine like a wood fiber and maybe some clay or soil, like a brick. But if we mix like a soil or clay with a wood fiber, wood powder, the percentage of wood is decreased. So we need to figure out, how to make like fireproofed wood 3D printing material, at the same time strong material for the real construction.
That would be very exciting. Also, I have a comment for Tanner and Nilüfer. Maybe they have tried it before. I don't know. I will just ask, have you ever thought about using tangrams instead of symmetrical patterns? Tangrams also would be very, very productive for the mold that you showed, also for the facade design.
Ayşegül, can you repeat that word? I'm not sure if I quite get it.
Tangram. You know the tangram play? Again, tangram.
Tanner, do you have any experience on this? Not sure if I know what the tangram is. That's the international language.
Well, it's okay. Actually, you're able to make many stuff by using it. It has, well, I will send a Google link. Well,
I just saw it. Yeah, I just saw it. So I think that's something that we realized towards the end of the study, and that's that final slide when we had mathematics and tiling was actually something that we realized it needs a very robust mathematical underpinning to be able to expand it and break away from regular grid type of pattern design for facade tiling. But that is actually a very interesting example that you showed me, because it seems that there is a limited number of geometries available, and then there is an infinite combinations. And that's completely in line with the framework of this research study, where we look into how we can control a limit variability to be able to use the cutting edge technologies in the current industry, which is not really open to employing those technologies and is sticking to their traditional methods because they are more cost effective. So it is, the study is right on somewhere between bespoke manufacturing and mass production, which doesn't incorporate any variability. But thanks for bringing up the point. Tanner, do you have anything to add?
Yeah, basically in our studies so far, we've explored a fairly simple grid layout in the hopes that it would bring to light some of the possibilities of this sort of variable pattern. But in the last slide, we showed that image of the Penrose tiling in which a large number of different geometries, you saw there were a lot of triangular or sort of almost rhomboid shapes that could still be interchangeable. And so moving forward, really hope to explore outside of just the square grid layout and see what sort of possibilities there are in the organization of more complex geometries with the system that we've sort of created. Thank you for your question.
Thank you. Are there any more questions? Or of course, I have a series of questions in my mind regarding the time limitations. I would like to ask one provocative questions regarding the future directions of those experimental approaches to all groups, maybe starting with Thomas. What do you think about the scalability of the workflow or technique you propose, like in a situation and requirement of scalability, scaling the workflow or maybe material or tools? Will we need like a larger or huge tools, or is there maybe, is it possible to bring some swarm way of scaling the those processes? What do you think about these future directions of scalability of like robotic weaving?
Yes, thank you for the question. Well, the first thing from my perspective is that the change of scale is never linear, right? It's always exponential. So if something is working in a small scale, it doesn't mean that it will work in the bigger scale, right? It's the typical example that we can have the difference of an ant and an elephant, right? Because an ant can lift like 10 times their own weight, but the elephant doesn't, right? So that means that that's the reason why in lower scale, let's say the superficial forces influence much more than the bigger scale. That's why we humans have bones. So that means that every time that we change scale from a small prototype, it doesn't mean that that change of scale will work. So one of the key things is how we can simulate a one-to-one performance in a using digital tools, and also how we can prototype this one-to-one using also robotic manufacturing processes. So one thing from my perspective is working directly in the one-to-one scale, that's for sure, and always to compare the digital prototypes with physical ones in a quantitative analytical process. And then that means that, of course, that working at bigger scale, we have the limitations of machines. As I showed in my research, it's typically like from, let's say, big universities or big research centers where they have abundance of resources. That is not the common for 99% of the universities in the rest of the world. So we cannot limit our creativity or creative process or digital manufacturing process to the investment of these big machines. So one good example is a project from Javlovina, I forgot her name, from Stuttgart, where she worked with these weaving robots. It was a master thesis like 2 or 3 years ago, where she used the idea of agents, of working with these weaving robots as agents, right? So somehow what she was doing, she was breaking the structural mechanical limits of a CNC machine, or the complexity of a robot arm, and she was bringing up to a very small piece that has a certain intelligence in order to be collective be fabricating collaboratively a bigger piece. That means that materials, it's all at the same time the machine, right? You can only beat something with the material depending on the tool that you have, right? So if you have a saw or a milling machine, we can inform the material in a certain and specific way, differently if we use another type of tool. So somehow I think that small scale fabrication, if it is smart and is totally advocated to the material's performance, then it can build up a much more bigger, let's say, a piece or one-to-one architectural scale, but always prototyping in that scale. Otherwise, the change of scale might break the whole process.
Thank you for this thought-provoking response. And maybe is there another one who would like to respond to the same question?
Maybe
Sure,
I can also
sure.
say something, since kerfing is, of course, as you have seen from the presentation, it has a lot of potentials in terms of shapes that you can reach, especially when you talk about kerfing. And so when the button is cut in only on one side, because you can combine polyconical developable surfaces. So you really have a lot of freedom, but then in the case of kerfing, you are very much limited from the self-weight of the components. So it really depends also from the final shape that the component has. It needs to be supported in a smart way. So it was a big limitation. But from this, we understood how the material was working. And so the upscaling of this is going to be the zipping that we are using to build larger elements. But we understood through kerfing how the wood is working, what are the geometrical properties that we had to follow, and the material properties, also all the moisturizing process that is very helpful when you are assembling in this kind of lab conditions. So when you don't have an industrial setup to make kind of complex elements. I think with the zipping, it's more possible because the resistance of the element is much more closer to a standard element. Let's say we are doing a lot of research in this direction. Of course, there is still this issue of the scalability. So as soon as you go with a larger element, I mean, you cannot just go with a larger section, apply the same principle, because, for example, we apply a bottom layer, which is the continuous layer of 3 millimeters in the case of the kerfing and 6 millimeters in the case of the zipping. But then when you go with larger elements, you cannot just increment this thickness linearly. You need to look to the bending radius, for instance. So you have a lot of parameters to include and to look. So every step you have to do, then you have to try many times in the lab what happens. So yeah, it's always, let's say, the final task is to try to see something which can be applied at an architectural scale, so at a one-to-one scale, but it's always very challenging, which is the nice part of this kind of research.
Thank you. Actually, I have an additional question to you, Dario. Since the participants of the next session doesn't interrupt us, we have some more minutes. Kerfing brings different potentials through augmenting the affordances of the surface planar materials. Even it is not easy to predict the end material behavior without testing it. In that sense, it also provides some potentials in form finding processes. And have you ever think about like how those material behavior will perform under extreme conditions, such as more pressure, underwater behavior, or some behavior without in changing or different gravities. So extreme conditions and curve bending surfaces. Have you ever thought about it?
So actually, after these experiments that we made with curving, we realized what you saw in the last slides with zipping, so these big elements, and we left them outside for 3 months, and I have to say they were quite fine, except the parts that were touching the ground, and they stayed in the weather in Denmark from September till 1 week ago. They were kind of still holding together. But in general, yes, it's not something that is directly applicable. So it would need for sure external layers or extra coating, which is what we didn't actually do in this phase. Probably also the kind of material that we used helped somehow, because we used an LVL for the zipping, and which was slightly coated outside with a thin layer of glue. So this helped also a little bit. Of course, there is all discussion about circularity and sustainability, because the more chemicals you add to this kind of structure, if you want them to be very easy to be recycled and so, the less they can be recycled. But yeah, it's also research in this direction. So for now, let's say it's more on indoor use.
Thank you. Are there any more questions to the presenters? I think until Fred say us stop, we can continue.
Yeah. No, if there is no more questions.
Last call for the questions.
Yeah.
I really don't have it.
Okay. But if you don't have any questions, it's okay, because we are on time.
Mm-hmm.
Thank you very, very much, Sema. Congratulations, all the presenters. And you invite you to the next panel. Is direct streaming from Chile. They are there in person, and it's a pleasure to it's a pleasure for us this session. Thank you very, very much.
Thank you, Sema, for moderating, and thank you all for presenting your interesting projects. Nice to meet you all. Hope we can do this in person next year or the year after.
Yeah.
Thank you all.
Yeah,
Nice to see you.
likewise. Yeah, thank you.
Thank you all so much.
Have a nice day.
Bye.
Bye.
Thank you.
Bye-bye.